Hi, this is the recording of the notes for a shortcut to derivative of polynomials. This year that it is day number 18. So quick video here. I'll try and get through these quickly, but hopefully this will help with your understanding. On these notes, problem number one, we're given a function f at x and we're asked to graph f prime at x. That is, if we knew the equation of this, f at x function, we would take the derivative and simply graph that equation. But we don't know the equation here. What I do know is that right up here, I can tell it that we have a slope of 0. So if I'm trying to draw the graph that represents the slope, that must have a value of 0. Right here, my f of x function also has a slope of 0. So my f at x graph, which represents the slope of f at x, my f prime at x must have a 0 in its graph. I know that this piece of the function coming up here from the beginning up through this maximum point has a positive slope. So from here to here, the slope is positive. So my function, that is my f prime at x graph, must have positive values. Between this maximum and this minimum, the slope of f of x is negative, so my f prime at x graph must have negative values. And this piece of the f at x function has a positive slope, so my f prime at x graph must have positive values. So without a whole lot of accuracy, I can say that this parabola-looking graph is a representation of f prime at x. The values of my f prime at x graph represent the slope of my f at x graph. I'll do something similar with part B, in that I know that if this is f at x has a slope of 0 here, and here, and here. So my f prime at x graph, which is the slope graph, the graph of the slope of f at x, must have zeros here, and here, and here. Now I'm going to need to connect these three zeros, knowing that the slope of f at x is negative. This is a decreasing function here. So the values of my f prime at x must be negative values. They need to be below the x-axis. Between this minimum and this maximum, f at x is going uphill. It has a positive slope, so my slope curve must have positive values and come back to 0. Between this maximum and this minimum, f at x is going downhill. It has a negative slope, so my f prime at x graph must have negative values. Similarly, from this minimum on out, this f at x is going uphill. It's increasing. It has a positive slope, so f prime at x must have positive values. So that's my f prime at x. So a little recap. First thing you want to find is where are the zeros of the f prime at x graph. They're where my f at x has a maximum or a minimum, because a tangent line at a maximum or minimum is going to have a slope of 0. That gives my f prime at x graph a 0 there. Okay, so this is like a birthday present to you right here. The derivative of the power function. We've done a whole lot of taking derivatives of, if I give you f at x, find f prime at x. We've had to use the definition of derivative, that whole limit as h goes to 0 of the slope, the f at x plus h minus f at x all over h. I'm giving you a shortcut. In general, if f at x is ax to the n, so something like if f at x equals 3x to the 5th, so a is our coefficient. We've got x to some power, and for my example I made it a 5. Then f prime at x is equal to an x to the n minus 1. So what I'm going to do is I'm going to take my a value and multiply it by my n. So I'm going to take the 5 times the 3. F prime at x equals that 3 times the 5. X to the n minus 1. So 5 minus 1. My f prime at x is equal to 15 x to the 4th. So great shortcut. Whole lot easier than doing the whole definition of derivative. So I'm going to take the exponent, multiply it by the coefficient, and reduce the exponent by 1. So a couple of examples here. First of all, I know that if I'm finding the derivative, if I'm finding the slope, this is a linear equation. And my slope, this is just y equals mx plus b. My m value is 2. But let's see if our rule will work the same way. My exponent here is 1, so I'm going to take the 2 times the 1. And the x to the n minus 1, 1 minus 1, is going to give me 2x to the 0. Well, anything to the 0 is just 1. So I've got f prime at x is 2. We knew that. Again, it's a linear function. So my m I can see is 2. Let's see if it works with our rule. F prime at x equals, well, the 2x, I already know that that's a 2. And this is an x to the 0. So I've got 4 times 0, x to the, doesn't really matter what, but it's 0 minus 1. This whole thing is 0, so my f prime at x is just 2, which I knew again up here. Same thing here. It's a linear function, so I know that m is negative 3. F prime at x is negative 3. I'm not going to go through that. But here I will. We've got f prime at x. Using our rule, I'm going to take the 6, the coefficient, times the exponent, and I'm going to get 12. X to the, I'm going to take 1 away from the exponent, make that a 1. So f prime at x is equal to 12x. A whole lot easier than that definition of derivative. Same thing here, f prime at x is equal to 6 times 2 is 12, x to the 1. And it really doesn't matter that I've added on some number on the back. And if we think about that, if I've got a parabola that's here or a parabola that's here, if it's the same 6x squared, it doesn't matter if it's in its normal spot, its parent graph spot, or if it's been moved down, the slope is going to be the same here or moved down. So we end up with the derivative being the same. That constant doesn't influence it. Our f prime at x here, 4 times 3 is 12. X to the 1 minus 3, 1 less than 3 is 2. So again, a whole lot easier than the definition of the derivative. So coming through here, I'm going to use my calculator for this. So let's see if we can open this up. I've got f at x equals 4x cubed plus 3x squared minus 2x plus 1. So I'm going to find my f prime at x equation while this is opening up. Now let's see if I can push a pause here. Okay, so I'm going to take my derivative, and I can take the derivative of each term separately. So negative 4 times 3 is negative 12. X to the 1 less than 3 is 2. Second term, 3 times 2 is 6. X to the 1 less than 2 is 1. Negative 2 times 1 is negative 2. X to the 0 is just a 1, so I've got the negative 2. And the derivative of 1 is 0. I've got x to the 0 that I'm going to multiply there. And I can also look at this as this negative 2x. If I just had y equals negative 2x, my slope is negative 2. If I just had y equals 1, the slope of that is 0. So here's my derivative equation. And here's my f at x equation. Erase some of this stuff. My f at x equation. And I'm going to take my calculator and put both of those equations in my y equals menu. So I'll clear that and clear that. So I've got negative 4x cubed plus, I'm going to pause this so you don't have to see me. Okay, so I've got both the f at x equation and the f prime at x equation in my calculator, and for some screwy reason I entered them in y2 and y3 instead of y1 and y2, but that's not going to hurt us at all. So I'm going to go to my Windows set, so table set, which is above window. And because this table starts at -3, I'm going to let it fill in for me. I'm going to start at -3. I'm going to go up by 1 and ask for an autofill. So when I go to my table of values, it gives me, at -3, I have 142. So I'm just going to take these values and put them in my table that's on the note sheet. So I just took the values off of my calculator table and was able to put them in the table of values here. So just for fun, I decided that I would graph this and see what it looks like. And if you look, I changed the window so that it fits the table of values that I've got in my notes. So I went from -5 to give me just a little bit more of a view, up to 5. Because my table went from -3 to 4 in my x values. And then my y values, the lowest y value I had was 215, so I gave this lowest value of 220. So again, I have a little bit of a border around there. And my highest y value in my chart was 142, so I went up to 150 on this window for y max. And when I graphed it, the red is my f at x, and my black is the f prime at x. So you can see that the red graph on here is a cubic, and the black graph looks parabolic. And you can see that where the red graph flattens out, I've got a 0 for my f prime at x. So just a little something to look at. Okay, and the last problem I'd like to do with you is, given this equation, find the equation of a line tangent to g of x. So this is going to go a whole lot quicker than they did before when we had to use the definition, but it's the same process. I need to find a point. I need to find the slope. And then I'm going to use point slope, y minus y1 equals the slope x minus x1. So my point, I'm going to need to find g at 1 because I'm asked for the tangent when x equals 1. So plugging that in, -4 times 1 cubed plus 2 times 1 squared plus 5x minus 4. When I do the calculations on that, that comes out to be a -1. So I've got that's a 4. Comes out to be a -1. So I have the point 1 comma -1. The slope, I need g prime at x. Well, now instead of having to use that definition and needing a whole lot of space here, I can use my new shortcut. -4 times 3 gives me -12. X, 1 less than 3 is 2. Plus 2 times 2 is 4. X to the 1 plus 5 times 1. X to the 0, and the derivative of a constant is 0. So now I want g prime at 1. I want the value of the derivative. I want the slope at 1. So I'll plug in my 1 here. 1 squared plus 4 times 1. There's no x there. Plus 5. What happens when you get distracted. So this should have been just a 5 because 5 times 1 and x to the 0. So g prime at 1 is -3, doing those calculations. So my slope is -3. So I've got taking this information of the x y1, -1, I'm going to have y minus -1 equals my slope, which is -3, x minus 1. So just tidying that up a little bit, I'd have y plus 1 equals -3, x minus 1. You're allowed to leave that in point-slope form. If you needed to rearrange it, certainly you could put it in slope-intercept or standard form, but I'm perfectly happy with it left in point-slope form. So I hope this helps. We can talk about it some more when we're together. Thanks. Bye-bye.